Okay, in this section, we're going to cover section 3.2, and that is on polynomial functions and their graphs. So a lot of this, I'm not going to cover this whole chapter. It's long. It's somewhat long, but I encourage you to look at it because there's some things that are interesting in there that might be helpful. But I just want to cover really like the essential material from this section. But yeah, as I said, this is a lot of the stuff we've already seen, but there are two things. There's the notion of a limit that I want to talk about, which is probably something you have not seen at all. So let me share my screen. Okay, so as I said, this is section 3.2. This is polynomial functions. And their graphs. So we're at this point we should be relatively familiar with a polynomial. So a polynomial, I'll just write it down again what a polynomial is, just for those who aren't quite as familiar with it, which is fine. So a polynomial function is a function of this form. So you have the an minus 1, a1 and a0 are coefficients, and you have these intermediate terms right here. There's a bunch of terms that occur between, and so these are the coefficients. This is the leading coefficient right here, and this is the constant term. And if n is not 0, then we say that this is an n-degree polynomial. So a polynomial of degree n. So first thing I want to show is, again, something we've seen already, but it's just good to reiterate and reacquaint with these things as many times as we can. The first thing I want to show is just some basic graphs. So I'm not going to try to draw these because my pen's not working very well at the moment, but I'll just open the book for you. So we have at least up to degree 5, we have the plot of these basic functions. So these are just like your elementary functions, and all the other polynomials will be some sort of combination of these more basic ones right here. So you have a first degree polynomial y is equal to x, second degree polynomial y is equal to x squared, whose graph is called a parabola. It's a quadratic polynomial. Then you have y is equal to x cubed, and this is its graph. Y is equals x to the 4th. And then we have y is equal to x to the 5th. It's a 5-degree polynomial. And you can see that there's some, with the exception of, I mean, even this y equals x has some similarity with x to the 3rd and x to the 5th. There's some similarity between polynomials of odd degree and polynomials of even degree. So if you look at let's look at the even degree one. So we have x to the squared, x to the 4th. They both look similar in the sense that, this one's a parabola and this is like the bottom's flattened out a little bit more. But what's the more important feature that they share in common is their so-called n behavior. What's happening as x becomes a larger and larger number, as x is getting closer to infinity, or as x is getting closer to negative infinity. When you look at, if you were to go out, quote unquote, go out to infinity, whatever that means, the graphs would look identical. You couldn't tell the difference between them. So this idea of a limit, they have the same limit as x goes to plus or minus infinity. The same thing with the odd degree polynomials. You have y equals x cubed and y is equals x to the 5th power. As you go out to infinity, as x goes out to infinity, as this x becomes larger and larger, the outputs become larger and larger too. When you cube a larger and larger number, as you cube larger and larger numbers, you get even bigger numbers, you know. So, and the same thing with x to the 5th. So we want to look at, we want to just kind of have a concise way of stating this. We want to have a more concise way of stating this limit behavior, this end behavior. So the nice thing about polynomials, let me actually pull the book up again, is that there are examples of continuous functions. And I think I mentioned in one of my lectures, it turns out if you look at the space of all continuous functions, this abstract infinite dimensional space of continuous functions, it turns out that every continuous function can in some sense be approximated from polynomials. So like they're like really all you care about, polynomials. No matter how crazy your function is, your continuous function, it can be approximated by polynomials. And yeah, so that's just this nice feature of polynomials. So understanding polynomials is important for when you go on into calculus or just study more generally mathematical analysis. And so the feature that they have is that they're continuous, and so, and in particular, they don't have any corners or these so-called cusps. So these first two graphs are non-examples. They're not examples of polynomials, but the last two are examples. So we want to better, in order to equip us for calculus, we want to, or some more advanced mathematics, even mathematics you deal with in engineering, say, we need to understand polynomials better. So for example, we're going to talk about trig functions, and it turns out, so I'm going to actually just pull it up because I don't remember it off the top of my head. But the trig function, if you plot it, it looks something like, or cosine, I'm sorry, if you plot cosine, it looks something like this. And it just kind of repeats. So this is y is equal to cosine x. So just to illustrate what I mean by this notion of approximation, it turns out that you can so this is cosine is defined on all real numbers. This is plot, so it's a continuous function. So if what I said is true about continuous functions, that they could be approximated by polynomials, then we should be able to do just that. And it turns out you can. You get this so-called Taylor series, and the Taylor series is an infinite polynomial. So it's Taylor. So if we have y is equal to cosine x, its Taylor series is the following. It's like it's alternating. So sorry, that should be a minus. And then the pattern repeats. So infinite polynomial. Oops. I'll just put that in quotes because it's not really like a precise notion. So this is the cosine function can be approximated by polynomials of this form, and the dot just indicates that this pattern repeats. This right here is not too bad. This is called factorial. So if you have n as a natural number, like 1, 2, 3, or 4, or 5, n factorial is just a product of all numbers from 1 up to n. So it'd be n times n minus 1 times n minus 2, dot, 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 times 2 times 1. So you have a multiplication here. So it's just, that's all this n exclamation point means. This is read as n factorial. It's just a product of all integers from 1 up to n. That's all that means. So 2 factorial is pretty easy, actually. 2 factorial is 2 times 1, which is just 2. 4 factorial is 4 times 3 times 2 times 1, which is 6, I guess 24 if I did it right. So yeah, polynomials are important. Every continuous function can be approximated by polynomials. And your computer, when it calculates function like trig functions and stuff like that, I mean, I don't know if all programs are in this way, but you can write programs that are based upon this Taylor series. So like when you calculate cosine of some number, you're not getting like the precise value. It's using this infinite polynomial, but it's only using it's using a large number of terms in the polynomial, but it's like cutting it off at a certain point because computers can't do an infinite number of computations. But the computer will give you a number that's extremely close to the actual value. So that's the importance of polynomials, if I haven't stressed that enough already. So one feature of polynomials that we want to look at is this limiting behavior, this n behaviors, so called n behavior. So let's look at an example. So we have, suppose we have y is equal to x squared. And I'm just gonna introduce some notation right now. What happens when x, so as I'm writing this down, I'm like telling you how to read this and interpret it. So what happens when x approaches or goes to infinity? Or what about when x goes to or approaches negative infinity? And the idea is that x, so you're taking maybe a sequence of numbers of values of x. So like, and those values of x are approaching or marching towards infinity. So you might take like 1, 2, 100, 1,000,000, 1,000,000,000, something, etc. You just keep taking larger and larger values, and you want to know what happens as x is getting larger and larger. What's happening to this function? And then we want to like give a geometric interpretation of that. So I think it's pretty clear, especially in this case, what's happening to this function right here. So as if you plug in 10, you get 10 squared, which is 100. If you plug in 100, you get, what do you get? I don't remember. No, it's 100 times 100, like 10,000 or something like that. I can't do arithmetic. So if you do 100 squared, yeah, you get 10,000. So you get a number that's even larger. So as x is approaching infinity, so as x approaches infinity, y approaches infinity also. And as x approach, what about negative infinity though? This might be a little trickier. What does y approach? Well, don't forget that y is equal to x squared. So no matter what you plug in, the output is positive. So you're going to take like x is equal to negative 10. Well, you square that and you get positive 100. Now you plug in negative 100. You square that, you get 10,000. Negative becomes a positive. So you're seeing the same, what we call is limiting behavior or n behavior. So in this case, y is still approaching infinity. And it's pretty clear how this works out geometrically. If I try to draw a graph, if we draw the parabola, it looks like something like this. And we're only drawing it on a finite inner domain, because the domain of a polynomial is all real numbers. So I can't possibly plot the whole thing, but we can indicate it with arrows where it's going, where it's approaching. All this is like language about limits. What happens to y as x approaches a certain number, or it approaches infinity. So as x is going along here, the y values are getting bigger and bigger and bigger. They're marching up because the graph is going like this. It's going towards infinity. And the same thing with x going negative infinity. As x goes this way, this graph is going upwards. So it's hitting all these y values. It's y is going to infinity. So we can express that more concisely with the following notation. So we're taking the limit as x goes to infinity of x squared, and we're saying that's infinity. So as x approaches infinity, x squared approaches infinity also. And the other limit is, the other notion or the other idea can be expressed in this way, is that as x approaches negative infinity, x squared also approaches infinity. So let's look at one more maybe non-trivial example, slightly non-trivial. So what happens if we have y is equal to x cubed? So what is the limit as x goes to infinity of x cubed? Well, it's the same principle. If you plug in a number and you cube it, you get an even bigger number. And then if you plug in a bigger number than the first number and you cube that, you get an even bigger number than when you plugged in that first number. So our intuition should be that this function is growing towards infinity. But what about this? This is a little bit different. What about when x goes to negative infinity? Well, this time we have to worry about the sign, because when you cube a negative number, you get a negative number back. So the idea is when x goes to negative infinity, you're getting quote unquote bigger negative numbers, although that doesn't make sense. Well, you might want to, maybe the better way to say it is that as x is going to negative infinity, the size or the absolute value or the magnitude of the output is bigger. So it's just and we express that by just saying it's a bigger negative number, even though that's not technically correct terminology. But it still expresses an intelligible idea. So the point though is that if you plug in -10, or say you plug in just -10, and you cube that, you get a big negative number. I don't know, you get 10 times 100, 1,000 maybe, -1,000. And then if you plug in negative number 100, you get a bigger, quote unquote, bigger negative number. So this limit is going towards negative infinity. And that's clear from the graph. If you plot x cubed, you get something like this. Not quite. You get something like this. So as x is going towards positive infinity, the graph is going up towards infinity. So we're getting all these. So y, the output at y, which is equal to x cubed, is going towards infinity. When x is going towards a negative infinity, this way, the output is going towards infinity. The graph is going towards infinity. So now it turns out that we have this nice dichotomy here with these limits. So it turns out that determining the limit really just splits into what is the degree of the polynomial. So I'm going to pull this, I'm going to open the book. There's a lot going on in this box right here. So if you take a polynomial, so this is our polynomial, then the degree determines these limits, or these n behaviors. So So the first of all, it's not just the, it's not actually, I'm sorry, it's not just the degree, but it's also the leading coefficient. So if we have it's split, as I said, we have this nice dichotomy. So the first case is that P is an odd degree polynomial. In the case of an odd degree polynomial, those limits are not going to be equal. So like in the case of x cubed, as x goes to positive infinity, you get positive infinity. As x goes to negative infinity, you get negative infinity. Of course, if you had y is equal to negative x cubed, the limits would switch. One would become negative infinity, the other would become positive infinity. But that idea that like the limits are opposites of each other is still expressed or still true in this case when P has odd degree. So this first graph here is when your leading coefficient is positive, so the AN right here. The AN is positive. So when that's the case, like for example, if you have x cubed, this almost looks like x cubed. The limit as, I don't know, can I draw on this? So yeah, here we go. So right here, let me just draw here. So what we're saying here is that the limit of as x goes to positive infinity of our function p of x, the limit is infinity. So this is, we're just dealing with the case when n is odd degree and the leading coefficient is positive. And then the other limit is the other limit, which is when x goes to negative infinity, that limit of p of x is going to be negative infinity. So this is just the x, the x cubed case here. And I should point out that this notation I'm using right here is not, as far as I know, it's not in the book. But I'm using it because one, it's just way more concise than the notation the book is using. And two, if you go to calculus or if you do any more advanced mathematics, you go into engineering, you go into any sciences, whatever, any sort of field of study that uses calculus in any way, this is the more common notation. This is used all over. This limit notation is very prevalent in mathematics because it's very suggestive. It indicates a lot what's going on. It's easier to read. So we're taking the limit as x goes to infinity of the function p of x, and we're saying that that's infinity, and then the other one says something similar. So this is the odd p has odd degree case when the leading coefficient is positive. So let me clear this. So now let's look at this case here. So let's summarize it using our notation. So in this case, p is still odd degree, but now the leading coefficient is negative. So think, for example, p of x equals negative x cubed. So the limits are going to switch. So we have the limit as x goes to infinity of p of x is negative infinity. And the limit as p goes to, or sorry, the limit as x goes to negative infinity of p of x is positive infinity. So the limits are switching. So that's p has odd degree and the leading coefficient is negative. Now let's look at p has even degree and the leading coefficient is positive. So this case right here. So this is x cubed or x squared. That's your model. Think of that case. And I should mention that the fact that we have these dots here or this dashed line here is just means that anything could be happening in this region right here. We don't know exactly what's happening, but all graphs under p has odd degree case and say leading coefficient is negative, they all exhibit this end behavior right here, this limit behavior right here. That's the sort of behavior that's the limiting behavior that they exhibit. So in this case, we don't really care what's happening in near zero on, if you want to use more technical terminology, we don't really care about what's happening to the function on a neighborhood of zero. Maybe you remember that a neighborhood of a point is an open interval containing that point. So what we don't, we are, what we're, so yeah, just to reiterate, we don't care about what's happening to the function on a neighborhood of zero, but what's happening outside of a neighborhood of zero. So on the outside of it. So what's happening as you're going towards positive and negative infinity. So in this other case, we have, in this other case, we're dealing with the polynomial have an even degree and the leading coefficient is positive. So let's just summarize what the graph is saying. So we're, in this case, so again, x squared is the paradigm. If you have an even degree and your leading coefficient is positive, then the limit as x goes to positive infinity is positive, and the limit as x goes to negative infinity is also still positive infinity, because when you have an even degree, it has to do with that fact that when you raise a negative number to an even power, it becomes positive. And then the last case is, we're still under the even degree case, but we have leading coefficient that is negative. And in this case, we can summarize the results as follows. When the limit as x goes to infinity of p of x will be negative infinity, and the limit as x goes to negative infinity of p of x is also negative infinity. They have the same sign. So why is that the case? Let's look at an example to get a better idea as to why that's the case. So let me pull this side now, and let's look at an example. So let's look at y is equal to x squared minus, I don't know, 5x. According to this table, so we'll say this is, actually, let's call this, we'll call this p of x, just to keep consistent with the notation, is equal to x squared minus 5x. Now, according to the table, when I take the limit, so the leading coefficient is 1, so that means it's positive, and the degree of the polynomial is 2, so it's even. So according to that table I showed you, we should have the following limits. These should be the limits. But why is that the case? Let's analyze the function a little bit more closely. So because you may think, well, what about this negative sign right here? Why doesn't that screw up things? Why doesn't that mess with things a little bit? Like, why do we have these limits? Why are the limits the way they are, even though we have this negative 5x right here? Well, the idea is that when x, so let's just look at x positive case, and the x negative case is going to be similar. Actually, let's start with the x negative case. That's really easy. So when x is a negative number, x squared will be positive, and then 5x, I'm sorry, I drew the wrong limits. This is not the right, they should both be positive according to the table. So let's try to figure out why the table is correct. When x is a negative number, so when we're in this case right here, when we want to evaluate this limit, not just by looking at the table, but not by looking at that nice table in the book, but like analyzing the function itself. When x is negative, x squared will be positive, and then negative 5x will be positive, because a double negative becomes a positive. So the overall function, P of x is positive when x is negative. So it makes sense that as you plug bigger negative numbers in, this limit is the output is just getting bigger and bigger and bigger. So it makes sense that this limit right here is equal to, the second limit is equal to infinity. But what about the first one? You might say, well, what about this negative here? Why isn't that mess up? Why do we get infinity? Why doesn't it mess this limit up somehow? Maybe why do we get negatives for some reason? Well, the idea is that as x gets bigger and bigger and bigger, it's true that this part right here is a negative, and that it's becoming a bigger negative number. But what's also true is that x squared compared to x is growing faster. It's getting bigger and bigger. If you plug in a table, like I'm not going to go through a table, but just draw a table, plug some numbers in, you know, 1, say, so you plug 2 in. Let's just plug some numbers in. You get 4. You get 3, you get 9. 4, you get 16. 5, you get 25. These numbers, the x squared numbers, are getting huge very fast, but x is growing very slowly. So although you're subtracting off, although you're subtracting off 5 times this first column, x squared is just getting bigger and bigger as x goes to infinity. So another way we can say that is that when x is very large, so when it's much bigger than 0, so let me just write this in parentheses, large, when x is a large positive number, we can say x squared dominates, so I'll put this in quotation marks because it's not a precise term, dominates the negative 5x term. So another way of saying that is that when x is a large, positive number, P of x looks like it's approximately x squared. This term becomes negligible. Negative 5x becomes negligible. So when x is large, P of x basically just looks like x squared. And so it's going to have the same limit as that. So what this implies is that the limit of x as x, the limit as x goes to infinity of P of x equals the limit of x as x goes to infinity of x squared. So when x is large, a large positive number, the polynomial P of x looks almost like x squared. So they're going to have the same limit as x goes to infinity. But we know what the limit of this is. We already know that limit. It's infinity. So that's why P of x goes to infinity. And so this whole long discussion was just to show why that table is true, why that table is correct. And you can play the same game with any other polynomial. You look at the leading term, you look at its coefficient, look at what's the degree of it, and then you can play the same argument. You can run the same argument. Oh, okay, well, when x is very large, this leading term is going to dominate the other terms. So really, when I take the limit of the polynomial, I'm just looking at the limit of the leading term. And so we can actually this whole discussion is actually, now this is not a proof. You have to prove this still. And when you go to calculus, you prove this. But this is like, mathematicians rely on proof, but also intuition. Like, what does this seem to suggest to say? What is all of this suggesting when I draw pictures? When I draw pictures, or when I do these numerical calculations right here, what does all of this suggest? And that's intuition. And intuition is a very important tool for a mathematician. So our intuition tells us the following. If you take the limit, I'm going to use a notation. So I'm going to express two limits with just one limit. So if you take the limit as x goes to plus or minus infinity, so I'm expressing two different limits with one notation of p of x, all you have to do is look at the limit of x going to plus or minus infinity of the leading term. That's all you have to do. And then this, so this right here, when you take the limit of this, it's always going to be infinity or negative infinity, depending on whether it's even or odd. And then you got to worry about the sign, right? So that's why you need the coefficient. That's for the leading term. That's why you need the leading coefficient and the x term. I don't want to write anything here, but that's what the whole discussion says. It says that when you take the limit of the polynomial as x goes to plus or minus infinity, it's the same thing as just taking the limit of x as x goes to plus or minus infinity of the leading term. Because of the same argument, when x is a large, say, positive number, that leading term dominates the other ones. So that's really what's determining the end behavior. It's just that leading term, which is a nice result, you know, because you can have a very complicated polynomial. It might have 100 terms in it. But when you want to determine the limit, what it says is that you can just ignore all those terms and just look at the leading term. And so it's a nice result. And when you go on to calculus or further mathematics, you can prove results. So the importance of this class is just developing intuition. Get a feeling for what a feeling for polynomials and functions and their behavior. And then when you go on to further mathematics, you use that intuition to make proofs of these various propositions that stem from your intuition. So I'm gonna pause the recording for a second, and then I'm gonna start recording. So this finishes 3.2, and then we're gonna move on to 3.3. Okay, so we're going to continue on to section 3.3. We just finished 3.2, which is on general polynomials and taking limits or to determine their so-called end behavior. So let me share my screen. So section 3.3 may seem somewhat boring and it's very computational. So there's not doesn't seem as interesting. There's not many maybe pictures associated to it, or at least the book will definitely not give you any pictures associated to the topics in 3.3. But it is important for when you get to calculus or further mathematics. So section 3.3 is on dividing polynomials. And again, there's this interesting interplay between geometry and algebra. You know, what is the connection between geometry and algebra? And for this, you might not think there's much connection to geometry. We're just dividing one polynomial into the other, but it turns out there is some interesting geometry going on. So when you get to calculus, you'll look at, we looked at limits as x goes to positive or negative infinity. But you will eventually look at more general limits. For example, suppose you have the function f of x is equal to 1 over x. So 0 is not in the domain of f. So the domain of f is negative infinity to 0, union 0 to infinity, to real numbers. But you will not be able to plug in 0. But you can ask, well, what's happening near 0? What happens as x gets very, very close to 0, but not actually equals 0, but it gets very close. And this is, all this is hidden or, more vague language of limits. So basically you're asking, when you ask what happens to the function as x goes near 0, you're asking what is the limit as x goes to 0 of the function f of x. So in this case, you got to be careful. Just like with infinity, you have to say, well, what direction are you approaching zero? Are you thinking of positive numbers getting smaller, 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 going towards zero? Or are you thinking of negative numbers that are very close to zero? Because if you, depending on your answer, depending on how you answer that question, you'll get a different value. So you have this notion of a left and right-handed limit, depending on whether you approach zero from the left or from the right. So let's look at the plot of 1 over x. So 1 over x, so let's just put a question mark. The plot of 1 over x looks something like this. You can plot this using Wolfram Alpha or, you know, whatever you want. So it looks something like this, though. You can plug in some numbers, make a table, or you can use a graphing calculator. It looks like this. So it turns out this limit doesn't exist. And it's clear from the picture. Well, as x goes, you consider x to the right of zero, going towards zero, the function is going all the way up to infinity. But when you consider x to the left of zero, so negative numbers going towards zero, the function goes down to negative infinity. So the answer, limit doesn't exist because there's not one single number. But you can distinguish them. You can say, okay, the limit as x goes to zero from the right, so we use the plus sign to mean to the right of f of x is infinity, or, you know, I'm going to actually put the actual function in. Let's see. So the limit of 1 over x as x approaches zero from the right is infinity. And the limit of x as approaches zero from the left. So the limit of 1 over x as x approaches zero from the left is negative infinity. So these are the types of limits you can approach. But you notice you have other limits right here. So that's what's going on near zero. But what about, say, when x goes out to infinity? Well, just from the graph, it's pretty clear that x is getting close to zero. And that makes sense. When you take 1 and you divide it by a really big number, you get a small number. And if you divide by 1 by an even bigger number, you're getting a number that's even smaller. So the 1 over x is shrinking as x gets bigger. So we have these other limits. And it turns out that these limits have an interpretation. What it means, so as x goes to plus or minus infinity, 1 over x goes to 0, it means that these are so-called, it says that the x-axis is a horizontal asymptote. It's a line. It's a line which the function approaches but never actually touches. So the function never passes through the x-axis because 1 over x can never be 0. There's no number x such that 1 over x equals 0. So the functions approach this. Now, this is a pretty straightforward limit to calculate. But it turns out for more complicated examples, you need to calculate the asymptote, whether it be a horizontal or so-called vertical, or a slant asymptote, you need long division. So let me see if I can pull up an example. of a function with a slant asymptote, and then we'll go through the example. We'll actually do the long division. So let's have a, so I want to just, if you read the book, none of this is in the book. And what I've said so far is not, I'm not going to test you on anything. I just want to motivate you, give you motivation for why we're interested in doing long division at all. So if you plug in, let's plot the following. This is x squared minus 9 over 2x minus 4. So that's what this plot looks like right here. And notice it looks like there's this slant line. It's even more obvious from this picture. It looks like there's this slant line which the graph approaches but never touches. It turns out that the slant line it approaches is the following: it is x divided by 2 plus 1. What happens when we plot that? See, look, it gets very close. So the graph approaches this very closely, but it doesn't actually hit the graph. Why is that? Well, why that's the case will be more obvious when you do this long division right here. So let's do the long division and then analyze the function. So let's look at, so our function is f of x is equal to x squared minus 9 over 2x minus 4. So now I'm going to introduce you to the topic of the chapter. It's long division. We want to perform this long division right here. And we're going to get a remainder, and then that remainder is going to actually, the remainder is going to be the slant asymptote. So this is, I'm going to run through the steps on how you do long division via an example. So you take the denominator. So this is, so you got the denominator, and then you put the numerator under this division bar. So this is like division as you did in, I don't know, middle school or whatever, I don't know, whatever grade it was. And the idea is you look at the leading coefficient of the, what is this? I actually can't always remember the terminology. So this is the divisor. This right here, the 2x minus 4 is the divisor. And then this right here, x squared minus 9 is the dividend. So this is the thing you're getting, that's getting divided up by this. So the steps are pretty straightforward. This is an algorithm. You can prove the algorithm works. We're not going to go through that. So the idea is, though, is that you want to look at the leading term of the divisor and then the leading term of the dividend and ask yourself, what do I need to multiply this by in order to get this leading term? So yeah, I'm sorry, it's the other way around. What do I need to multiply the divisor by so that the, no, this is not quite right. Hold on for a second. Yeah, so the question is, what do I need to multiply the divisor by so that the leading coefficient, or the leading term, matches the leading term of this? Well, that's pretty clear. If you multiply by 1/2 x, then you'll get x squared, which this 2x will become x squared, which is the leading term of this. So let me get rid of some of these lines so it's confusing. So then what you do, so once you've identified that, then you actually multiply this by you multiply this thing you determine right here times the divisor. So that gives you x squared, and then you subtract that from the dividend. So 1/2 times x times this will be x squared, but then you got to negate it. And then 1/2 x times 4 is going to be 2x, but then you negate it, so it becomes a positive. So it becomes 2x. And then you combine these. And then this becomes your new dividend in a sense. So you get, when you combine these, you get 2x minus 9. And then you play the same game again. So this is the new dividend. So when you have to ask yourself, okay, what number do I need to multiply this by so that the leading coefficient of this matches the leading coefficient of the new dividend? Well, it's simple. It's 1. So you multiply by 1. And then when you do that, you multiply 1 by the divisor and you subtract it from the new dividend. So you get 1 times 2x minus 4 is just 2x minus 4, and then I negate it. So you get 2x plus 4. And then when you add these together, you get 5. So now the degree, this is another polynomial. Notice that each time we divide, we get a new dividend, and it's another polynomial. The algorithm terminates, it stops or it terminates when the degree of the new dividend is less than the degree of the divisor. So the degree of 5 is less than the divisor, which is 2x minus 4. And then you have, what this means is that R5 is the remainder. So this right here is the remainder. So what that means, I'm sorry, it's actually -5. So what that means is that you can write the function, which is equal to, what was it? It was x squared minus 9 over 2x minus 4. You can write that as 1/2 x plus 1 plus the remainder. So you got this piece right here, and then you add the remainder divided by the divisor. So if you combine these fractions, you will in fact get this right here. And then it's pretty clear that when you take these limits as x goes to plus or minus infinity, that you get the sort of behavior we saw in the graph. So the idea is that when x is large positive number, for example, when x is a large positive number, this right here, remember, 1 over a large number is small. So as x is getting bigger and bigger and bigger, this remainder right here is getting smaller and smaller and smaller. So it's becoming dominated by this term right here. This is becoming smaller, this piece right here. It's shrinking. So when x is a large number, what this says is that f just almost looks like it's approximately 1/2 x plus 1. So that's why the graph of the function gets very close to it. But since this is an approximation, it won't actually equal. This will not be an equality. Not at least always. It's not always the case that's an equality. But this will be an equal. It says that when x is large, the function almost looks like this line right here, and that's exactly what we see. Let me pull that up again. So when you graph these again, remember you get that the function as x is getting bigger, as that you're going along this way, the graph is getting very close to the line, and that's even more obvious in on the first plot when I first plotted it. So look at right here. It almost just looks like the line 1/2 x plus 1. But it won't equal it, but it'll be approximately equal to it. So as x gets large, the function just looks like the line 1/2 x plus 2. So in this case, the 1/2 x plus 1 is you call this the slant asymptote. So this is why we care about, for one reason why we care about the division algorithm. And hopefully that makes sense, and this will help. If you can understand this will help you tremendously for when you go to calculus. So let's look at one more example of long division, and then we'll call it a day. So this is example 1 in the book. I'll just run through the algorithm one more time. So we're asked to divide. Actually, maybe I'll go through another example after this. So we're asked to divide 6x squared minus 26x plus 12 by x minus 4. So this is the dividend, and this is, let me scribble this out. So this first polynomial is the dividend, and then x minus 4 is the divisor. So let's set this up. So we have the divisor goes here, and then under this is where the dividend goes. And then we play that same game. So we have the dividend here. We want to ask ourselves, what number do I need to multiply this by so that the leading term of this matches the leading term of the dividend? Well, that's pretty clear. It's just going to be 6x. So now I'm going to multiply that through. So I'm going to multiply 6x by x minus 4 and then subtract that from the dividend. So if I do that, I get negative 6x squared, and then I have negative 4 times 6x, and then I have to negate that, so that'll become positive 24x. And then I combine these two to get the new dividend. So this cancels with this, and then I add this to this, I get negative 2x plus 12. And then I have to do the same game. So this is my new dividend right here. That's my new dividend. I had to ask myself, what number do I need to multiply this, the divisor, by so that the leading coefficient matches the new dividend? Well, that's pretty easy. I just got to multiply by negative 2x, or just negative 2. So if I do that, I get negative 2x, that becomes positive 2x. And then I have negative 2 times negative 4, that becomes positive 8, but then I have to negate it, and so it becomes negative 8 again. And then if I combine these, I get 4. I should get 4 at least. And the degree of this new dividend is less than the divisor. So this is the algorithm terminates. So then what this says is that, so this is, I think the terminology they use here is this is the quotient. And then this is going to be our remainder. And of course, we can take another way of saying this is that we have, actually, because I'm going to do this part, I'm just going to go through this one example. Another way of expressing this problem is that we have the following fraction and we want to decompose it. So we have 6x squared minus 26 plus 12, and we're dividing it by x minus 4. And because of the above work, we can decompose it in the following way. We write the quotient first, so it's 6x minus 2. And then we have to add the remainder, which is 4. The remainder divided by the dividend, which is x minus 4. And if you go through, if you combine these two fractions right here, you should get that the left-hand side equals the right-hand side. So that's, as I said, if I were just to present just a division algorithm, it'd be kind of unmotivated and boring. Like, what's the point of doing this? But there's a very clear geometric reason for wanting to do this especially when you get into calculus, because you want to determine the end behavior of a given function, a rational function, like the first example, this example up here. We were given this rational function, and we want to determine the end behavior when x goes to plus or minus infinity. I only looked at the end behavior as x goes to plus infinity, but you could look at it as it goes to negative infinity as well. I'll leave that to you. And to determine that, you need to do long division, because it's not clear. Because if you plug in x, so if you were just plug in x equals negative infinity, you would have infinity over infinity, but that doesn't make sense. This is called what they call in calculus an indeterminate form. It doesn't tell you anything about the end behavior, because infinity over infinity is not defined. But you can rectify the situation by doing this long division and then taking the limit, as we did. So we did the long division, we decomposed it in this way, and then we took the limit. We let x be a large positive number, and we saw that so it does approach infinity, but it approaches infinity in this way, in the same way that 1 over x plus 1 does. So that's the important point. We don't care just that it approaches infinity, but we want to know, say, the rate at which it approaches infinity. How quickly does it approach infinity? And it turns out that the function behaves like this thing right here. The function behaves like 1 over x plus 1 when x is a large positive number. And we could only see that by doing the division algorithm. So hopefully the division algorithm makes sense, and hopefully the reason why we do the division algorithm makes sense. Of course, you don't have to worry about these slant asymptotes and these limits and stuff like that. I just wanted to share that just to give you the motivation for why we do this. So I'm going to call that quit. I'm going to turn this recording off now.